For the second part of section 2.8, we're going to be doing things that are amazingly close to what we did in part 1. If you look up here on the screen, you can see we've got in green our function. And we'll have a first x value that's right here, x naught. We're going to slide over delta x to the right. There's x naught plus delta x. And of course, you will have a corresponding y value of f of x naught for x naught. This can look a little busy right here, but your y value would be f of x naught plus delta x. And then, of course, we can definitely look at the change in these y values, that's delta y. We also have, most definitely, a very important tangent line right here, and that's in red. And we've got our point of tangency. But you can see we're also using dy there. And we're going to talk a lot about dy and delta y and what that really means. First of all, I want to let you know that dx and delta x are the exact same thing. What you're going to see is delta x is going to be the change in x on the curve going from one point to another. Dx technically is the change in x on the tangent line. Whenever you see something called a differential with a d, that will be change, but in the tangent line. Very, very, very important to point that out. See that letter D, you're talking about change, but on a tangent line. Delta, you've seen that a lot. In science classes, delta always meant change. Delta x is the change in x, delta y is the change in y, but that would be on this green curve here. You want to talk about D's, differentials, that's change on the tangent line. Well, we've been using differentials a long time. We've been saying dy dx is the derivative, f prime of x naught. That's the change in y on the tangent line all over the change in x on the tangent line. Change in y over change in x is what we think of as slope. This is the slope of our tangent line. But let's just say that I multiplied both sides by dx. We'd have dy is f prime of x naught times dx. But like we just said earlier, dx and delta x are really the exact same thing. So we have this wonderful formula. This is something you want to memorize. dy, the change in y on the tangent line, is equal to f prime of x naught times delta x. And this is a wonderful way to talk about change, but change on the tangent line. So let's take a look at a problem right now where for number 2, we have two things. We want to find delta y for this function. And for part A, delta y, plain and simply, is really just y2 minus y1. And in fact, what we're going to see is, if you look at the top of the screen here, that's f of x naught plus delta x minus f of x naught. And we're just going to work this out and find a formula. Now remember that we have f of a blank is equal to 2 blank squared plus 9. And whatever we're putting into these spaces on the left, we put in on the right. With that in mind, we'll have 2 x naught plus delta x squared plus 9. That's f of x naught plus delta x minus, well, what's f of x naught? It's 2 x naught squared plus 9. And real quickly, just a quick reminder of some algebra. If I gave you a plus b squared, that's a squared plus 2ab plus b squared. And we're going to really work that out right now. Let's keep our 2 out in front, but this will become x naught squared plus 2 x naught delta x plus delta x squared. Then I'm going to have to multiply by 2. And after I distribute a 2, I'll add a 9. Here I'm going to begin to just distribute this negative This part isn't nearly as tough. We've got minus 2 x naught squared. Distribute a negative here, you get a minus 9. I'll distribute the 2 to everything in here. We'll get 2 x naught squared plus 4 x naught delta x plus delta x squared. I hope you can see some good canceling taking place. The minus 9 and the plus 9 are gone. A 2x naught squared and a minus 2x naught squared are gone. What does that leave us with? Well, plain and simply, 4x naught delta x plus delta x squared. More to the point, even more importantly than just writing this formula out, this is the change in y on the curve, the true change in the y values on the curve. Let's take a look at the differential dy. And by the way, look up here in this blue box what's been highlighted. We're going to say dy is really f prime of x naught times delta x. Well, if f of x is equal to 2x squared plus 9, guess what f prime is? Hopefully that's plain and simple and just a 4x. Well, let's plug in our x naught. We'll get 4x naught delta x. And that, nice and simply, is our differential. That is a change in y also. However, it's the change in y on the tangent line. So very, very important for us to see the difference. By the way, also note the amazing similarity. Both of these do have a 4x naught delta x in them. Now we're going to take a look at a little table here. If you're dealing with the exact curve, delta y is y2 minus y1, or y1 minus y beginning, y naught. That's the change in y that you'd see from 2 points on the curve. The approximation for that, which by the way you can see up above, is actually a very simpler formula. And this is why we can use differentials. dy is plain and simply f prime of x naught delta x. And that is the change in y on the tangent line. Relative change. As you talk about change might sound big, but really, to be able to have an idea as to how much we've really changed, we have to compare it to our beginning y value. So we'll take delta y all over y naught. That's our relative change. If you want to find your relative error, so to speak, with an approximation, you'd have dy all over y naught. And then finally, to deal with the percent change, you might wonder just how much you've changed percentage-wise. Take your relative change, or your relative error, and multiply it by 100. So how can this be of help? Well, let's take a look at our last problem. For example 3, we've got a sphere. And we've got this big sphere right here. We've got a radius. And they're telling us that the radius of that sphere was found to be 21 centimeters. However, there could have been a measurement error. Maybe you were plus or minus 0.05 centimeters too big, too small. If you made an error with the radius, clearly there would be an error with the volume. So we're going to use differentials to help us. First of all, if we're going to talk about volume, the volume of a sphere is 4/3 pi r cubed. And we're going to actually use this idea of dy equals f prime of x naught times delta x. The thing is, what we're really looking at is this is our function. You could call it f, or you could call it y. But really, I'll just keep it as a v. But it's not a function based off of x, dependent on x, it's dependent on r. So what we can do is say dv would be f prime of r naught times delta r. Well, if this is our f, let's go ahead and take a derivative. You'd bring down a 3, and that would cancel, and you'd have 4 pi r squared. And that's really what we're going to have for our f prime. Now our r naught is 21. So we'll have 4 pi times 21 squared. That's our derivative plugging in our beginning radius. Delta r, however, is how much our r could change. We could be 0.05 bigger, 0.05 smaller. So we're going to put in a plus or a minus 0.05. Let's work this out and find out just how big our dv might be. We'll have 4. Then we can type in pi 21 squared. Then we can say, let's delete that, bring that down, say times 0.05. You can see we're at about 277.088. 277.088 cubic centimeters. That's how much error we might have in the volume of the sphere. Now, at first glance, that might sound to be excessive. That might sound to be really way too big. The big question is this a serious error or not? Well, that's where we're going to have to go to our relative error. Our relative error is always going to be dy over y prime, or in this case, dv over v prime. We already know what our dv is. We found that down below. The question is, what is v prime? Well, v is 4/3 pi r cubed. Let's go ahead and work this out. And we can say alpha y equals, and say, well, here's your 4, and here's your thirds. And we'll say pi, and it's 21 to the third. You can see we've got about 38,792.386. So, as we're looking at that, we're going to say, well, 277.088 divided by that, just how much error are we really speaking of? Well, we've got our 277.088472 and so forth. I'm going to say divide that by second answer, and we've got 0.00714. So that's going to be our relative error. If you want to find your percent error, you multiply that by 100. So it's 0.714% error. Really, that's not that bad. And, that's where just looking at the size of dv isn't sufficient. You really need to put things into perspective, comparing that to the original y value.